Hi there, welcome to this topic on metric relations, which is one of the most common topics on both the multiple choice and short answer sections of the exam, mostly the short answer, and also the long answer portion of the exam where we see questions involving multiple triangles that are stuck together. And so metric relations is a really vital topic for us to consider here in this help video. So I put a little diagram, an instructional diagram up top where I ask you to consider the following right triangle. ABC, where BC is the base and AH is the height. What you might notice about this is that AH is an altitude and BC is the base, but that the base is actually the hypotenuse of a right angled triangle. So if you see that there's this right angle here, opposite a right angle is a hypotenuse, and we're going to use that as the base of this metric relation. Now, metric relation questions are recognizable by the fact that they have an altitude cutting this right angle up here at the top that I've circled. And so whenever you see a question that has a right angle with an altitude dropped from it or cut through it, that's always kind of like a little hint where you can think to yourself, oh my goodness, this is probably a metric relations question. That altitude has to drop down to the hypotenuse and make a right angle with the hypotenuse, which becomes the base of the relation. Now, if I take that over to this diagram here, we know in right-angled triangles that we have two legs, so these are labeled L1 and L2, and we have a hypotenuse, as I mentioned before, which is labeled H. Now, I know some teachers use A, B, and C, but I find that much less intuitive than remembering that there's two legs and a hypotenuse to a right-angled triangle, something we all learned in grade 9. Now, as well, A is labeling our altitude, and then the two segments that are formed by the altitude dropping down to the hypotenuse, we call these letters M and letter N. And while I haven't provided the derivation of this using similar triangles, this series of relationships of the various segments of a metric relation can be defined by this series of formulas to the right. So L1 squared equals M times H, L2 squared equals N times H, and A squared equals M times N. And of course we have Pythagorean theorem here at the end, and that's to do A squared plus B squared equals C squared, and that's both legs squared equals the hypotenuse squared, and you should be familiar with that. So here's an example below which covers a little bit more terrain than the typical short answer question. Usually short answer questions are giving you M and N and asking for A, which is a very direct question on the short answer, but I want to explore finding maybe multiple unknown sides just so that we have a little bit of a richer question here. So there's a number of ways to go at this question. I notice that we're given 5 and 3 over here, but we're given none of the other sides in the triangle. Now, here we have a right angle. If there's a right angle on the one side, there's going to be a right angle on this other side as well. So for some students, using Pythagorean theorem would be the best way to go to find A, and it's true. If C squared equals A squared plus B squared, I could say that 5 squared equals 3 squared plus B squared, and that's going to be my altitude. That's actually A in our diagram. And that's fine. And so I could do that out. Subtract 9 from both sides. You get 16 equals B squared. And therefore your altitude in this diagram is going to equal 4, and that's quite helpful. Now my next question might be how do I find the values for L2, N, and H? Well, I notice that I do have A and I do have M. right? This one was L1, just to put all our labels on the picture. So if I want to use the relationship a squared equals m times n, I might be able to find out n, because I already know my a and I know my m, in order to get n. 4 squared equals 3 times n. So 4 times 4 is 16. Don't do 4 times 2. That's incorrect, and I see it often. It's 4 squared. Okay. Now 3 hugged up against n, that's multiplying, so it's opposites dividing. So I'm going to write this n equals 16 divided by 3. It's going to be a decimal, and that's okay. 5.33. I'm going to just always keep 2 decimals for these things. Okay. And that's great. Now what else do we need to find? Well, I notice that h is the entire base, or the hypotenuse of the right angled triangle, and we do have the 2 lengths that make it up, so we can just add those together. So that's convenient. And then last but not least, we have a couple of options. We could do L squared equals n times h. That's an option. We could also do Pythagorean theorem for the entire outside perimeter of this right triangle. We've already used Pythagorean theorem here in this example, so I'm going to use the L squared formula to find this missing value right here. So let me do it below. So L squared equals L2 squared equals n times h. So L2 squared. I can put brackets there so the 2's don't look confusing. N times h. I've got L2 squared equals, and let's get a number for that. It's like 44.3989. Now that's not my answer, that's L2 squared, so the opposite of squaring is to square root. I'm just going to move our question down here and give us a little more room. So L2 is going to equal the square root of 44.3989, which equals 6.66 approximately. Now there's no units given in the question, but you can always just say units, if given that situation. Now, as I said, metric relations questions are extremely common in the short answer portion of the exam, and so I really want you to be able to work with these. So make sure these formulas up top are on your memory aid. All right, so we'll take up more metric relations and how to solve long answer questions using triangles.